is a professor at the University of Bonn. To continue the theme from Terry's talk, this will be a second talk about big collaborations in the context of formal mathematics. His title is the Carleson Project.
Thank you very much, and thanks to the organizers for organizing this very nice event and allowing me to speak. So I'll be talking about the Carleson project, which is formalizing Carleson's theorem, which is a result in harmonic analysis. I'll talk a bit later about what the actual result is. But actually, I think I want to start with how did we organize this and what is the story of how this project came about. And then I'll end a bit with some lessons learned, design decisions, formalization lessons we've learned. So the result that we're interested in is Carleson's theorem, which was proven by Leonard Carleson in 1966. And this was extended then over the years. So this was this is a result about the Fourier analysis. It was extended by Hunt in 1968, and over the years, harmonic analysis still looked at variance for variations of the Fourier analysis, Fourier transform, and changes generalize this result. So in Bonn, there's the harmonic analysis group led by Christoph Thiele, who proved a new generalization of this. And they were interested in these formal tools, and so we started the discussion, can we formalize this? So I joined Bonn in fall 2023, and we discussed some collaboration to formalize, and we chose this result as generalization of a milestone result in harmonic analysis. And actually we started in the way that Terry just told us how not to do it, namely just taking the paper, trying to write the formula. I tried to start formalizing the proof directly, and this quickly ran into issues because my background is not in harmonic analysis. I'm not an expert in the field, and so I had to ask continually questions like, how does this step follow? What are you doing here? And this went very, very slowly. And so we decided what we've also learned from other projects, and what we've now heard multiple times here, that we used, we started writing a blueprint. So the harmonic analysis group spent some time to take their proof and write a much more detailed version of the proof, which blew up the total size of the proof by a factor of 4. So that happened in early 2024, and at the same time I was formalizing the definitions that we used and some of the statements, and then in June I launched the formalization to the public, and I basically said, hey, this is we have now this nice blueprint. I formalized a whole bunch of statements. If you want to join, you can just take one of these lemmas and formalize it. And I was very surprised by the response, and quite a lot of people joined the formalization quickly. And so actually, in the early months, there was a lot of progress all at once. So from June to September, we hit a milestone that 50% of the lemmas that we had written down were already done. Those are, of course, the easy 50%, and progress has slowed down afterwards, but it's still going strong, and we're nearing the end, although we're definitely not yet done. So let's see what we're talking about. So we have a single dependency graph for the whole project. So there's not much you can see here other than the average color of the bubbles, which looks pretty green overall. And so this is sort of the hierarchy of the proof. So the main result is over here, which is the generalized version that we're proving as its main result. Then this giant area on top and a little bit here is proving this main result. And then the part here and the part here on the right, that is deriving sort of the classical version of Carleson's theorem from the main result. So the statistics are that we're now there's in total 179 lemmas we have to formalize, and there's 28 of them still missing. So I haven't done the math, but that looks like we're sort of 80% done, and I mean I think we have a very clear path to the end. So there's only 12 results missing for the main theorem, and then there's a bit more missing here for the reduction from the main theorem to the classical theorem. In the repository there's now 126 sorries, which is interesting because I posted 2 weeks ago on the Zulip that there were 88 sorries, but that is due to sort of an ongoing refactor that Michael Ruff, here in the audience, is doing, which temporarily increases the number of sorries. So it's interesting that sort of if you look at sort of the sorry count in the proof, so this is the number of lemmas or steps in lemmas that are omitted. That is not sort of monotonically decreasing, but can go up, because sometimes after a day of hard formalization, you've managed to reduce one gap to 10 smaller gaps, and that is progress in the formalization, even though it increases the sorry count. And yeah, so I think sort of this is a huge success in sort of collaborative effort. Yes, as I said, in June of last year, I launched sort of this public formalization. And how we typically worked with this is that I stated sort of the formal statement of a particular lemma, and then there was a detailed LaTeX proof that was visible online. So we use Patrick's Lean Blueprint tool, Patrick Massot's Lean Blueprint tool to have a nice rendering of this LaTeX blueprint in your browser, so you can easily read it and link to it, which was very convenient. And so then contributors used read the blueprint, read the relevant definitions, which were easily hyperlinked, and then could sort of figure out sort of what the proof was, and then code it up into Lean. And a lot of people joined this group. So the blueprint was written mostly by the harmonic analysis group in Bonn. So Lars, Oscar, Regula, and Christoph. So they wrote this very big blueprint, and then the formalization, a lot of people joined. So some of them who are here, so Maria, Leo, Sebastian, Evgenia, Edward, Pietro, Jasper, Jim, Michael, James, and Jeremy. They all did a substantial amount of work, and then there were also contributors that just did maybe a single lemma or made small contributions here and there. And and what's interesting about this is that sort of the people that were part of this formalization effort, most of them don't have a background in harmonic analysis or even analysis. And that put sort of a constraint on the blueprint. So the blueprint had to be so detailed that even as a non-expert, the obvious steps had to be written out so that you didn't have to reinvent them on the fly. But yeah, so that led to some struggles, but where sometimes the proof was not completely clear for a non-expert, but mostly this worked very well. And and contributors could prove some lemmas of the project by studying the blueprints. We used a slightly more primitive version than what we saw in Kevin's talk or the equational theories project, where I just posted like a giant list on Lean Zulip chat, the chat room, to say like what are the outstanding tasks, and people could claim the tasks. So here are all the tasks that I posted like 2 weeks ago, which were 2 weeks ago all outstanding, and so you can see that here there's now already a couple of those that are done, and quite a bit more that are in progress. And so all the tasks here marked as in blue, those are still unclaimed and need to be done to finish the result. But we're now at the stage that sort of every definition and every lemma in this project has been stated, and we're just waiting on about 30. I mean, we're still working on like the remaining like 30 lemmas to finish them before we can like claim success and finish the formalization. So this and you can see from the numbering, which is sort of I've here removed sort of all the completed tasks from before I posted this, and in total there were like 158 like separate parts that like individual tasks that people claimed. So more about the blueprint. So the original proof of this result was about 30 pages, which we never actually which we haven't made public yet. So we once the formalization is done, we want to like make a regular publication of the original like mathematical results. With the extra statement, oh, this has all been completely verified, and then we'll make a separate paper on like, we'll write a second paper on the formalization effort and everything that went into that. These 30 pages, this became like 120 pages when writing out all the details in the blueprint. And then there were 30 more pages added to like derive sort of the classical version of Carleson's theorem as a corollary from the main results. As I mentioned, this really helps contributors to formalize all these results. And what I also found interesting is that actually some of the contributors, they were still learning Lean, they were still relatively new to Lean, but sort of this was a good maybe second project for them to like work on as, for example, contributing to Mavlib is sometimes I've noticed quite scary for like newcomers, because Mavlib has like these very high code standards, and sort of for parts of this formalization, I'm not as strict about sort of what I accept as a proof, as long as it compiles and sort of is like maintainable code. I'm happy to accept it. And so there were a few contributors that were also quite new to Lean and didn't know the harmonic analysis and could still, with effort, like successfully contribute. So I think that was very nice. One thing that is tricky is that if there's sort of a mistake in the formalization, it's harder to figure out how to fix this, or if and it's harder to sort of state results in the appropriate generality. Like when we want to formalize, and have like a reusable formalization. We want to state things in like in appropriate generality so that it can be applied to other things. And this is like significantly trickier if you don't know the area. Like how do you state something in proper generality? So what we did in this project, mostly I stated many of the lemmas, and then many of the preliminaries we stated in a lot of generality, so that and then we have the aim to put that into mathlib, but then sort of the core of the proof we are not attempting to like try to put into more generality, and yeah, we don't have like the ambition to put sort of the main proof in mathlib. Yeah, so that is what I mentioned here. So for the sort of the main part of the proof that we don't for the part of the proof that we are not intending to put into mathlib, we're not following all the mathlib standards of code quality. But then, so as preliminaries that we want to put into mathlib are, for example, operators with of weak type and strong type. Jim Portuguese wrote like formalized the real interpolation theorem, which was very nice in like proper generality, and we want to put that in mathlib. So then we have a nice formalization of the Hardy-Littlewood maximal principle, Hilder van de Korpet, Hilbert kernels, and so there's plenty of material that we will put into mathlib. I think once the sort of the main result has been formalized. So I've talking mostly about the sort of the organization, and I want to sort of transition to like what the mathematical result is. So let me recap, start by recapping well, the main main definition in harmonic analysis, namely that of the Fourier transform, because the Carleson theorem is like a very difficult proof on the Fourier transform, so Carleson's original proof was very difficult, but it sort of has withstood like much of simplifications, and sort of every later proof of extension still has sort of a very difficult core of in the arguments that is difficult to state, and it's a notorious result for that reason. So the Fourier transform, so say you have a function from the real numbers to the complex numbers to be concrete, and say that the function is integrable, then the Fourier transform is take the function multiplied by this complex exponent of e, which is linear in x and a new frequency variable xi, and then you integrate over x, and you get a new function in xi. This function has in nice cases an inverse, which is very similar except for the missing minus sign in the exponent. Yeah, we have this inverse function. And so how we think of these operators is that sort of it breaks this function down into components along these frequency functions, these complex exponentials. You can make this precise if you think about L2 functions, so square integral functions, and then you're breaking up sort of the function as like sort of as a linear combination of these basis elements, these complex exponentials, but these complex exponentials are not actually L2 functions themselves. They are not square integrable themselves over the whole real line, and so you cannot just take sums of them, but you can take integrals of them and break it up this way. And this interacts very nicely with differentiation. So the complex exponentials, they are eigenfunctions for the differentiation operator. If you differentiate one of them, you just get a constant multiple of them back. And that means that the Fourier transform for nice enough functions also interacts nicely with differentiation. So it turns the derivative of a function just into multiplying the function by the variable, the frequency variable, and some constant. And this is sort of one of the main powers of the Fourier transform, that it turns problems about derivatives, so like differential equations, into just polynomial equations in the frequency variable. And this is why the Fourier transform is used a lot. And we have the Fourier inversion theorem. If like the function f is nice enough, then if you apply the Fourier transform and then the inverse Fourier transform, you get exactly the same function back. But if the function is just integrable, then the Fourier transform always exists, but might not be integrable. And you have to be a bit more careful about what this Fourier transform, this inverse Fourier transform even means of a non-integrable function. So this happens also already in very simple examples. So if you have just a box function that is 1 on the interval -1/2 to 1/2 and 0 outside, then the Fourier transform already has this like oscillatory nature that is not integrable on the whole real line. And then we can modify the definition of Fourier transform a little bit to talk about and take improper integrals. So instead of integrating the function over the whole real line at once, which requires integrability, we can integrate the function over just a finite interval and then like let the interval go to infinity. So we take an improper integral, and this works for any locally integrable function. And then we have to be a bit careful what we mean by the topology here. And there's a few natural choices. So one thing we can do is just do pointwise convergence. So for a particular R, and for like a particular psi, take this value and just take the limit of all these values as R goes to infinity and see if this converges. Or you can view this entire integral as a function of psi and see whether it converges with respect to the LP norm. So the LP norm is just take an integral of the function to the power p, and then take the 1/p outside the integral. So this gives a semi-norm, and you can also look whether this this improper integral converges with respect to these norms. And so, for example, the Fourier inversion theorem says that for L2 if you start with an L2 function, then the Fourier transform is again well defined with respect to the L2 norm. If you take this, so you take this limit with respect to the L2 norm, and the Fourier transform of the function is again an L2 function. So that means you can take the inverse Fourier transform, and that gives you the same function back if you considered this limit again with respect to the L2 norm. So with L2 functions, everything is nice. And the Carleson theorem asks, what do you get if you look for pointwise convergence, what sort of other reconditions on your function? So if the function is continuously differentiable, say, then pointwise everything is also nice. But what if you remove some conditions and you ask, what happens if I just start with a continuous function or even an LP function? And the Carleson theorem says for if f is an L2 function, then if you consider these Fourier transform and the inverse Fourier transform with respect to pointwise limits, then this equation holds. So applying the Fourier transform and then the inverse Fourier transform to your function f gives you the original function value back for every point except on a set of measure 0. So for almost every point. So Carleson proved this for L2 functions, and then Hunt 2 years later extended this to all LP functions for p greater than 1. So for p strictly greater than 1, unless they're equal to 2. And so this, I won't go into the proof, but I want to sort of give you some ideas why this might be a quite tricky thing to prove, and that is that sort of all these ingredients in this theorem statement are necessary. So you cannot, so you can find examples of particular square integrable functions that where the sort of this equation doesn't hold on sets of measure 0, and actually for every set of measure 0 you can cook up some function where it fails on that, at least that set. So it can fail arbitrarily badly on sets of measure 0. And also, I mentioned, the function has to be LP for P strictly greater than 1, and it fails catastrophically for like L1 functions. So there are L1 functions where sort of this, the limit describing this, this expression actually diverges for all points. So, so for L1 functions, this is completely false. And also, if you just naively translate this to like functions in more variables. So currently, this is only for the theorem is only for functions like from the reals, say, to the complexes, or at least the domain has to be the reals. But if you consider like functions that that take 2 arguments or multiple arguments, whether this holds depends very much on in which order do you take the limit. So, like, what is the shape of your integration domain that you then blow up to infinity? And if you take, for example, squares or cubes in higher dimensions, like this theorem is still fine. But if you take other integration domains, this is much more complicated. I mean, I believe this is still an open problem if sort of you take a sphere as your integration domain and then blow this radius of the sphere up to infinity. So that's yeah, kind of interesting. So to give you a glimpse of how this is proven, is that sort of the main argument in a proof is that you define like certain operators. And you want to show that they are bounded. So this is one version of the Carleson operator where you take a function, and this looks a little bit, if you squint, of the integral defining the Fourier transform. So it's still, you're taking the integral over a function, you're multiplying it by some kernel, in this case 1 over x minus y, and then you're multiplying it by a complex exponent. And you, in these operators, you often like take some kind of supremum over various values. And you want to know that sort of this operator is bounded with respect to like certain LP norms. So suppose you put an L2 function in here, is the resulting output sort of, again, an L2 function with where the norm of the transformed function is like bounded by the norm of the original function. Up to some constant. So that is sort of the main ingredient of the proof, and sort of every proof of Carleson's theorem shows that some operator like this is bounded, and then derives Carleson's theorem as a corollary. And that is also by far the hardest part of the proof. So what we do in this generalization is that that we actually prove that a much more general operator is bounded than this Carleson operator. So, so this is roughly the original Carleson's operator, but actually there's a little bit of trickiness here, namely that this integral again might not exist, like if x and y are either too close to each other, or if you allow integration over all of the real numbers. So again, to be more precise, you have to integrate only again over bounded domains. So in this case, an analysis of where x and y, the distance between x and y is between 2 values. And then you integrate of that, and you also take a supremum over these the bounds of your integration domain. And then in the generalization, we are actually generalizing a lot of the components of this. So instead of like talking about multiplying by a particular function, this 1 over x minus y, we can talk about like a general class of so-called Calderon-Zygmunt kernels that have some properties about like their arguments. They cannot blow up too quickly when you go to infinity. There must be some continuity in one or both of the arguments. And we can prove that this operation is bounded for a whole class of these Calderon-Zygmunt kernels. Also, very often what is considered in harmonic analysis is not just the Fourier transform, but some extension of the Fourier transform, where instead of like just a linear function in y, you consider maybe polynomials in y or other functions in y. So we have a collection of functions that we call compatible functions, which just satisfy a list of abstract axioms where we can prove that this operator is bounded. And then actually we generalize from the reals to setting of so-called doubling metric measure spaces, where we have a metric space and we have a measure, and the measure interacts nicely with the metric, which means that sort of if you take balls of a certain radius, like the measure of the balls with 2 times the radius cannot be too much larger than the measure of balls of radius r. And then in this generality, which is what we use for the general Carleson theorem, so what the Bonn harmonic analysis group proved 2 years ago, actually this operator we cannot prove that it's bounded in all cases, but there's some conditional bound. So there's a much simpler operator that we assume to be bounded, and then we prove as a result that this operator is bounded. So then to prove sort of Carleson's original theorem, we still have to prove that for the real numbers that simpler operator is bounded. So now let's show a little bit of lean code. So this is one of the targets we have for classical Carleson's theorem. So here we stated slightly differently for the Fourier series instead of the Fourier transform. But so here, so this is the classical Fourier Carleson theorem in lean. So we have a function. In this version, the function f is continuous and periodic, and then we have these partial Fourier sums you take. So you look at the Fourier coefficient, and then you take the original function back by its Fourier by the sum of these coefficients, and if you let sort of the number of coefficients that you take go to infinity, then this converges to this is the neighborhoods of your original function value for almost all x. So this for all subscript m is the Lean's way of to say for every x except for set of measure 0. So this is the current classical Carleson that we're aiming for. We also want to extend this a bit. So, for example, we want as separate corollaries that f is just L2 or like LP, and also to do this for the Fourier transform. But that is not part of the original blueprint, but sort of a separate goal further that we want to do later. So let me also briefly flash the main result. So this is the fully generalized Carleson theorem. So I don't want to go through all the details, but we have like these compatible functions that I mentioned, these that occur in the exponents of the Carleson operator. So and here we're saying, okay, this Carleson operator is sort of bounded by some expression, conditional on that like some other operator is bounded in some way. So I don't want to detail this, go into detail here, but just to flash you the sort of the main results. And so I wanted to do a little bit of a progress report. So the blueprint is written in 11 sections, and actually, yeah, we're making good progress. So in section 1, we just state the main result and sort of all the definitions for it. So there's nothing to prove there. Section 2 sort of distributes the work into like 6 independent parts. And there's also a few lemmas that are then used throughout the proof. This was already finished like 1 month after the start of the formalization. And then like 6 sections are devoted to proving each of these 6 propositions, and those are completely independent of each other. Here I'm not doing chronologically the sections, but so 2 of the sections are sort of mostly independent results that we use in our proof, that are sort of preliminaries, and we do definitely want to put into Mavlib. So we needed a result called Hulder van de Corput and the Hardy-Littlewood maximal function and the Hardy-Littlewood maximal theorem. those were all finished in April this year, mostly by Michael Rothgang. Well, so Polder van de Corporate was done by Michael Rothgang and Sebastian Guezel, and the Hardy Little maximal function was mostly done by Jim Portuguese, which by himself formalized the whole real interpolation theorem, which was very useful for this. And then sort of 4 sections are really the core of the proof. So the proof roughly goes by taking your this metric space X and sort of tiling it into like small finite pieces, which we call a grid structure, and then similarly doing something similar for the frequency domain, where we also have something called a tile structure. And this sort of breaks up the proof on the whole space into like these smaller finite pieces. So first we have to construct this grid and tile structure. That was already done very quickly after the start. Then the next section is sort of categorizing these tiles into how difficult they are, and there's sort of 3 categories we have, and here we prove sort of the easy deal with all the easy tiles, which was finished early this year. And then the sections 6 and 7 are sort of the main part of the proof, where we deal with the 2 hard cases of these tiles. And there, we're done. In section 6, Maria Ines, who is in the audience, has done like most of the work and is 2/3 of the way done, sort of. And section 7 is almost done and deals with the other hard case. And so this is really the core of the proof, and I'm very happy that like how far we are. And then section 3 puts it all together. So. I mean, section 3 sort of reduces like some more specific setting to like the general setting, and we only just barely started with that. So, but I don't see actually like any difficulties here. Like this is a much shorter and somewhat conceptually simpler part of the proof. So I think this will go smoothly, and this is all that is needed to formalize the general statements. And then there's 2 sections devoted to like concluding the classical statement, and we're making good progress there, but there's still quite some things to do. So this is sort of the current progress report. So I'm very we're doing very well, but I think we still need a few more months to like completely finish this. And so the last part of the talk. I want to talk a little bit about design decisions, so what have we learned from this formalization, what we can use in other analysis formalizations, like how do we formulate things better. So one thing that I already mentioned is these LP spaces, so these are these functions that have like a finite LP norm. When you work with them, you typically quotient them by identifying 2 functions that are almost everywhere equal. This is nice, or at least this is done because sort of everything you do respects almost everywhere equality. And then you consider, for example, linear or sublinear operations between these like LP spaces. And these are then in general sort of like Banach spaces, or in the case that P equals 2, like Hilbert spaces. And this actually, if you do this directly in Lean, this turns out to be kind of annoying, and that is because, well, if you identify functions up to almost every equality, then sort of function application is not a well-defined operator anymore, and I mean, you can sort of choose an arbitrary witness and define function application this way, but then, for example, like equations you want like this don't hold anymore, where like the witness associated to f plus g might not need to be everywhere equal to like fx plus gx, and this will only hold for almost every x. And this is sort of very annoying to work with in Lean, at least at the moment. So maybe this can be done with better with nicer tooling, but currently this is sort of a pain to work with. So in this project we worked with functions that are defined just everywhere, not with quotients, and we just have the properties that the functions are like L2 functions or LP functions. There's a downside to this, and that means that sort of the abstract machinery we have about like functional analysis don't directly apply to these cases. So there was a recent case where we had to talk about like adjoint operators and use a particular result about adjoint operators, which we sort of had to do by hand. Yeah. So, but overall, I think it's much nicer to work with these actual functions. That does make it nicer. Another thing that I learned is how to deal with sort of a somewhat technical issue on like how to deal with basically the real numbers. So there's sort of three types that you often work with when doing measure theory or integration, namely the ordinary real numbers, the non-negative real numbers, and the non-negative real numbers with infinity added. So this these are the notations in Lean. This is notation for just the interval from 0 to infinity, including infinity. This last one is very natural when you work with measures, because measures take values into this type, like they can be infinite. And of course the first type, just the reals, is very natural, and then the non-negative reals are kind of convenient because they like are sub-object of both of them. But if you just work in analysis, there's the risk that sort of every lemma chooses like its own place where to live, and you have to like translate between those types like all the times, which I mean doesn't sound that hard, but can get quite annoying if you like have to translate expressions from one to the other like in every proof. Again, this could be maybe solved by better tooling, but I think this can also be solved by like making like a very well chosen design, like when to use which one. And this is actually a place where our project did not do very well, because originally I thought, okay, let's do everything in the real numbers. Like everything we're doing is basically finite anyway. And like we'll take supremums, but we'll prove that they're finite. We'll take integrals, but it's only over like a bounded domain, so this is finite. And then we just don't have to worry about these other two. But actually, this turned out to be the wrong decisions, and it's more annoying to work this way because you have to prove the finiteness all the time. So, for example, if you take a supremum, you have to prove that the supremum exists for it to be nice. Well, if you take supremum in the extended non-negative reals, that is just always nice and it always exists. And then you can later at some point prove, oh, the supremum is actually finite. And so actually during the project we transferred most of the argument. Instead of talking about the reals, we started talking about like these extended non-negative reals. Yeah, so now actually we are working mostly in the extended non-negative reals. This is also because Mavlib likes to work with operations in the extended non-negative reals, so it was much easier to use sort of all the Mavlib results. And actually some operations were infinite in some cases, and or maybe on a set of measure 0, and then, or we didn't know yet that it was finite on all cases. And so this brings me to the last point. So as part of the proof, we talk about the Hardy-Littlewood maximal function. So the Hardy-Littlewood maximal function is roughly this, or at least this is one version of it. Where you take a function, say from the reals to the reals, or the reals to the complexes, and you integrate. So the maximal Littlewood function at x looks at every ball either centered at x or containing x, and then you sort of take the average of your function value on that ball, and then you just take the supremum over all balls. This function has some nice properties. In particular, if your original function is integrable, then this maximal function is almost everywhere finite. And so how do you, but it might in some cases be infinite. In some, at some points it might actually be infinite. And so actually the maximal function does lie in these extended non-negative real numbers. And how do you prove that the function, this hardy little maximal operator applied to f is almost everywhere finite? Well, you show first that it's like something called weak L1. So basically it's weakly integrable. And from that you can conclude that it's almost everywhere finite. And what's interesting is that in MAVLib, so we had these L1 spaces, but L1 spaces were only defined for functions that have as codomain like a Banach space. So saying that f is an LP function, when we started the project, required that the codomain of the function was a normed vector space. And so this works well for real valued functions, but it doesn't work well for like functions in like the extended non-negative reals, but because that is not a normed vector space. And so even to state that the maximal Littlewood function is like L1 or weak L1, we had to modify it already a little bit. So this is the lean notation to say like, oh, take this this number in the extended non-negative real numbers and like turn it into a real number just by sending like infinity to 0, say. And we could state and we proved that this is an L1 function, but this doesn't actually tell you that sort of the original maximal, like the original function is almost everywhere finite. Like it could be that this is just infinite, almost like in many points, and you've turned them into like zeros of the new function, and showing that that function is integrable doesn't actually tell you anything about its values at infinity. So to even like do this argument, we had to extend the definition of like being an L1 function to also include the extended non-negative reals. And so what we decided to do is we just add a new class called enorm, which associates to like a type just a function into the extended non-negative reals. This is a so-called notation class, so we have an associated notation with this. So this just describes that you have some kind of function and some notation with it, but without any axioms. And this is also what we do, for example, for norms. And there's two instances we are particularly interested in, namely all the normed spaces and like the extended non-negative reals. And this is actually sufficient to define what it means for a function to be integrable or to be an LP function, because you just look at well, the Lebesgue integral of like the norm of a function. And then, but to prove then things about it, you need to some axioms. So, for example, you might want to consider like in what we call now an enorm space, where you assume that besides this norm you have like some monoid structure on E. We don't ask for a group structure because of course the extended non-negative reals don't have a group structure. And we could say, oh, maybe this is a module not over the real numbers, because again that's not true for the extended negative real numbers, but maybe it's a module over the non-negative real numbers. And then we have some axioms, so the enorm is maybe continuous. I think I should have added like a topology as well on E. And then some axioms for the norm, like maybe some kind of triangular equality, some kind of like norm property, and how it respects with scalar multiplication. And an ongoing refactor of that Michael is mostly doing is actually changing a lot of like mathlib results about integration, about like LP functions to sort of this more general class or like a subclass of this with only with weaker axioms. And actually most of sort of basic measure theory still holds in this setting. And that allows us to like apply it to both to functions that take values in the extended non-negative real numbers and for functions that just have take values in say Banach space. Yeah. So and I think we've also sort of learned in the formalization that yeah. So this norm E subscript E is this notation for E norm, and that turns out to be like a very natural operation in measure theory, and actually using this simplified quite some proofs. Yeah, so let's end. I want to end on this. So in conclusion, I think that that formalization is really suitable already. Like we're at a stage that we can formalize like serious research in harmonic analysis, like current research projects. So this is in contrast to some other areas where this is not feasible because you have these giant towers of like number theoretic definitions you need to build first, which seems to be less of a bottleneck in analysis, although we're definitely also still missing like definitions in analysis. And I think this formalization, this setup with formalization projects that that are guided by a blueprint, and then people can like take small parts and yeah, do collaboration this way with Lean and a blueprint is very convenient. And yeah, there's some nice design decisions we've identified for analysis. So I want to end on that. Thanks for listening. Shall I do the questions?
I'll let you handle the questions.
So I guess there are kind of complicated computations in the project, and at least if you click on a random bubble on the dependency graph, some statements look pretty scary. Could you comment a bit on that on the big computation side? Maybe, I don't know if you can show some code, or maybe tell us if you wished for better tactics to handle computation.
Yeah, so yes, there are so a lot of the proof is indeed with these estimates where we bound like some function by indeed some pretty big constant. So so yeah, these computations are yeah.
Very good. Very good.
They are a significant part of the proofs. I'm not sure sort of what I would ask for like as automated tools for that. So one thing that would definitely be very nice if sort of like standard tactics like ring and linear riff also works for the extended non-negative reals. That is one of the disadvantages, is that sort of the like ring doesn't work for the extended non-negative reals anymore, at least not as well. And
Norm doesn't for NN reals.
I'm not sure about that. Maybe. Yeah. So having sort of like support of already existing tactics for NN real, that would be very nice. And I mean, so other automation that I think would be very nice is like proving integrability side conditions, more reliable like extensions of funprobe to prove like measurability and so on. I think there's quite a lot of work we're doing manually there that is quite straightforward and could be automated. Okay. Yeah.
So first of all, thank you for that. Oh, wonderful. Really nice. I had two questions, somewhat related. So the first one, you mentioned at a certain point that you don't aim to push your results, or most of them, to mathlib. But Carleson's result, at least the classical one, nice very much. So if you can comment on this. And the second question I had was about the L1 case. So you mentioned that Carleson's failed miserably in the L1 case, and I was wondering whether this is something that you can prove using your project, or if this is completely unrelated perhaps very easy to see, or
Yeah. Okay. So your first question on what part we want to put into Mavlib. I mean, I think this is also a discussion we have to do with like the Mavlib community. Like, how do we want to deal with these kinds of projects? So, sort of the state is sort of like many of the preliminaries we've already tried in advance to sort of do them in proper generality so that we can move them to Mavlib easily, but we haven't done this for sort of the main proof. And the reason for that is just we're lacking sort of it's hard to do that either for the people in harmonic analysis, or what does it mean to be like proper Mavlib generality. I don't think that is like a notion that mathematicians think about a lot. Or, I mean, because it's a little bit different than the mathematical generality, I think. And also, like, I and other contributors don't really have the expertise to generalize the current results to, like, proper Mavlib generality. So I'm thinking more about, like, yeah, we probably don't want this in Mavlib because it's, like, a giant amount of code that is not following Mavlib style and would be like a lot of work to put into Mavlib style. How we want to deal in Mavlib with recording that this final result maybe is formalized but not in Mavlib. Maybe we can have some methods for still recording that even though we don't have the fully formal proof in Mavlib. That might be something to consider. Your other question about L1 functions. So I mean, it would be quite different to show that, like, there's an. I think it's not particularly hard to give an explicit L1 function where just this equation just always fails, but that would be quite different. You see in the formalization sort of that's where it goes wrong, like proving that it is working, because like sort of the constants they blow up as if your function is LQ, then like sort of the constants blow up to infinity when Q goes to 1. So you can sort of see the behavior there as well. Yeah.
So this was more for a remark, but so you're saying that it's very difficult to work with n and ring, and because then you have to cross between n and in and ring. At the same time, in my project, I've noticed that it is really annoying to use the n and ring because I have constantly to check that things are non-zero and not infinity. And the thing is, I started daring into Mavlib, and then Sebastian Wesen went to NPR and said, well, you know, in Carleson, we found that it was much better to use Henry than Henry. Do you not think we should not stick to use EAP now rather than defining more non-negative grid permutation? And so, what do you think of the two approaches coexisting? Do you think it's doable, or there's no point?
I would prefer if from experience I think that sort of just working with Ian and Real is more convenient, except that we're lacking some tooling. So there are in the last few weeks improvements to the finiteness tactic, so that can hopefully automatically discharge most of the side goals that things are not infinity. And I would prefer to see direction in sort of like adapting like existing tactics or having more tooling for like solving the issues for that you've encountered working with Ian and Real than like having the two systems coexisting. Because if you have the two systems coexisting, then you inevitably, I mean, then either we have to duplicate sort of all the results in both systems, or you have to transfer between the two again, like quite often, and that is also inconvenient. Yeah, Bas?
Two questions, a big one and a small one. So one is in Big Proof 1. I mean, we were really motivated by the big formalization, the Kepler conjecture, and the hot book. So you've now pointed out that you can do another big formalization. So what have we learned from Big Proof 1 to Big Proof 3? The other one is more specific. So you've chosen to formalize elements of LP to be functions, but they're really elements of quotients, as you pointed out. And this gives you problems with infinity. Could you do, I mean, this is one of the,
What do you mean it gives me forward
because you force them to be functions and not elements, of, abstract elements of LP, you need to deal with infinity. Could you get around that if you don't make that choice and just have abstract elements to make a more algebraic theory?
No, so let me start with your second question. I don't think if, so for example, like proving that a Hardy-Littlewood function is almost ever finite, like showing that it is like actually an LP function, this, like you would still have to prove it even if you do the other way. Like you have to prove that it's an element of LP, I mean you still have to do the work. So I don't think like sort of this choice of talking with working with pure functions actually affects that. Yeah, yeah. I mean, and your other question, so what have we learned since Big Proof 1 and Big Proof 3? I mean, I think the main lessons is that we've learned that like we can create this giant collaborative library mathlib, and that supports can support many formalization projects, including now like current research in harmonic analysis, which I think would have been very difficult at Big Proof 1.
Thank you.
We are minus 2 minutes in, so we should go and have our break, I think. Would you like to say a question or something else?
Maybe one comment on the previous question and then I start. So about the question of should we put everything into Mathlib, I want to point out that both the Mathlib maintainer team and also the Lean FRO are really thinking hard about how to scale up the Lean ecosystem and Mathlib and all the formalization projects to just being 10 times or 100 times bigger. And it's clear that in this process, I mean, we won't stay forever with everything goes into Mathlib. I mean, there are people working hard on make it feasible also for big projects to depend on Mathlib and not big project being maintainable while being outside of Mathlib. There is work going on about it.
Yeah, that's a good comment as well.
So I've been reminded we have a group photo also, although I don't know where. Ah, we've got an expert.
Yeah, so we're just going to all go outside, so we'll make our way out that way.